Hi, and welcome to Geology 112, Dinosaurs and the Age of Reptiles. I'll be your instructor for the semester. My name is Dr. Joe Peterson, and I'm a member of the Department of Geology here at the University of Wisconsin-Oshkosh. This course is actually the second stage of a two-part geology sequence that most of our students here at UW-Oshkosh do. So, for example, you may have had physical or environmental geology in the past, and that's a first geology course, and the second would be either this course, Dinosaurs and the Age of Reptiles, or Evolution of the Earth, Geology 109. So if you've taken 109 and now you're taking this, make sure that you understand that you're only going to get credit for one of them. Regardless, though, I want to welcome everybody to Dinosaurs and the Age of Reptiles, and I want to remind you that this is a geology course. So while we will be talking a lot about dinosaur behavior, evolution, functional morphology, we are also going to be talking a lot about how we know those things from the geology in which we find dinosaur bones. Before we get too far ahead of ourselves, it's probably a good idea to go through some of the basics of the course. Again, my name is Dr. Joe Peterson. Dr. P is totally fine. My office is in Harrington Hall, room 211, and I will be holding office hours Monday, Wednesday, Friday from 11:30 to 12:30 or by appointment. Now, these will be a mixture of digital or virtual office hours and in-person office hours. I will be updating our Canvas site for the class with when we'll be switching back and forth from that. I just want you to know that if you have questions or if you need to get a hold of me, I'll be making myself as available as possible. We do have a lecture textbook for this class. It's Spencer Lucas's 6th edition of Dinosaurs, the textbook. We won't be following through this book page by page, but I want you to have the book as another reference to rely on along with the lecture notes and these lecture videos and the review sessions. It's just another good reference with another way of kind of describing some of these concepts. Now, normally I do a lab manual for this course, but since we're doing it predominantly online this year, I've decided to just put all of our labs online. So when it's time for a lab meeting, check Canvas and print off what you need to, and we'll kind of go from there rather than go buy something at the bookstore. So class hours and lecture is a little tricky because normally this class would normally meet 3 days a week in person, but since we're doing it mostly online, what I'm going to be doing is posting weekly lectures, and I'll try to get those out Monday or Tuesday of every week. And then we will have some kind of scheduled review session in person that's totally optional that I'll be, again, announcing once we get some information back from registration on room assignments. Again, just to reiterate the point that I'm trying to make this course as accessible as I can, and if that means having an optional moment to meet in person, we can do that. Otherwise, we can kind of stick to safety protocol and do most of this online. Now, that all being said, lab sections will meet in Harrington 114. You should be signed up for one of two lab sections, either a 1:50 to 4 Thursday or an 8 a.m. to 10 a.m. Friday lab section. I would like you to stick to the lab section that you are assigned to. If you have to change, just let me know ahead of time and we will make appropriate arrangements. Now, how are we going to do lab sections in an age and time and world where we are social distancing? The reason we're doing lab meetings, and it's not for every week, but for a number of them, is because geology and paleontology, for that matter, are sciences where you really do need to see things in person. You need to be able to touch them, be able to move them, and look at them under light. And there's a textural relationship with learning the material and having handled some of these specimens. Now, in order to do that safely, I'm actually going to be giving everybody 2 weeks to complete a lab. So, for example, if you are in lab section 1 that normally meets 1:50 to 4 on Thursday, you will have 2 weeks, two Thursdays to come in and look at the material. Most of the labs will be material that you'll read at home and do work at home, but then you can briefly come into lab to take your pictures, take your notes of lab specimens, work with the materials, and then go home to complete the exercise. So I'm going to be giving you 2 weeks per lab to get it completed and to come to class. So if you don't want to come week 1 to lab, that's fine. Come week 2. It's just a way of reducing the number of people in the classroom at one time, and it gives me time in between to clean everything up. If you have any questions about this, please let me know, but I will be announcing more details about this as we approach lab. And to give you a little bit more information about myself, I'm a vertebrate paleontologist and I actually study dinosaurs. And I also do open up research opportunities to students. So if there's anything we're talking about in class or something you read that you find interesting and you're considering doing a research project or helping out with a research project on one of those topics, please let me know and I'll be happy to accommodate you any way that I can. Currently, I'm doing research on the big long-necked dinosaurs like Apatosaurus. I'm also doing some research on T-Rex because everybody loves T-Rex and it's cool. And also I do a lot of taphonomic research, which is a subfield of paleontology, where I actually look at how fossils actually form. So this involves looking at dinosaur skeletons, such as Allosaurus at one of our main dinosaur quarries in Utah, and sometimes also doing some really gross experiments with modern chicken bones. Of course, because dinosaurs and birds are closely related, we can do these types of experiments on modern organisms to learn a little bit more about what happened in the past. So if you're interested in shooting dinosaurs with lasers or digging up bones or learning how to prepare fossils or coming up with some research ideas, please feel free to reach out. I'm always looking for another interested research student. As I mentioned a few moments ago, this course has been modified into an online modified instructional format. So it is going to be partially synchronous, partially asynchronous. Normally we would meet 3 times a week in a lecture hall and then once a week for a lab exercise. But how we're going to do that to accommodate the COVID-19 pandemic and to maintain social distancing standards and adhere to CDC recommended health regulations, we're going to be doing things a little bit different. So lectures will be posted on Canvas. Again, I'll be doing the lecture for the week, and you'll have the week to review it and take any notes, and I'll be leaving them up so you can always go back, but try to keep up with the weekly lectures. You do not need to attend any in-person lectures. We're not going to be doing that. However, make sure that you understand you are responsible for having all of the material under your belt. Make sure you are reviewing the lecture content throughout the week. If you have questions, it is your responsibility to ask me and reach out and tell me I'm having a problem with something. I will be holding office hours. Again, Zoom style video conferencing, phone, email. These are times when I'll be at my computer, staring at the screen, waiting for somebody to call. I might even be doing some open Zoom style meetings where you can log in and chat with me as you need to. I'll just be sitting there. Other times I will actually be in my office and you can come visit me, and I'll be announcing that as we go through the semester. Okay, if I have office hours today, it's going to be virtual or they'll be in person. If you need to see me, let me know and I'll make that work. We're also going to be doing some optional weekly review discussion sections in a lecture hall. I'm trying to get a room that's large enough to accommodate everybody, but my anticipation is we probably won't have everybody in there at once. But maybe we'll do it on a Friday or something. This will be a weekly optional review session. We'll use the scheduled lecture time to do that. And I'll be making more announcements about that too as we get those details together. So for the lab component, there's going to be 6 lab exercises, and about half of these will require you to actually come into lab to look at rock, mineral, or fossil specimens. But again, you'll have 2 weeks to do this, and it won't be the entire 2 hours of lab time. My idea is that you'll do these in phases. You'll go through the lab exercise units in phases. A completed lab is 10 points. So if you're enrolled in the Thursday 1:50 to 4, you've got 2 weeks to come on Thursday from 1:50 to 4. Think of it more like an open house for 2 weeks to do that portion of the lab. There's more details about this in the syllabus, which I strongly recommend you read very carefully. So for the lab component of the class, I'd like you to complete the labs in 3 stages. And again, this is going into part of that maintaining those CDC guidelines. Stage 1 is to just do the pre-lab reading and answering the pre-lab questions, and you'll find these on Canvas. So when you download or start going through the lab exercise on Canvas, you'll notice that the first part is a lot of reading, or not a lot of reading, but some reading, and then answering some questions. And then you'll be prompted at one point to then go into the lab to do in-lab data collection. So this is when you would go to one of the two class sessions over the 2 weeks and take pictures, take notes, whatever you are going to need to complete the exercise at home. And then finally, the last part is the analysis and the reporting, and that is completing the exercise at home based on the data that you collected from stage 2. Think of these 3 stages of completing the lab exercise to doing an actual research project. When I'm studying fossils, I will do a lot of literature background readings and jot down what my main hypotheses are. And then I'll go to a museum where I'll spend some time there looking through the collections and taking measurements and photographs and laser scanning of the fossils that I'm looking at. And then I go back to my office or I go home to actually complete the research project and write the paper. I don't sit in the museum collection the entire time to do that. So we're going to be emulating that same kind of process with the lab exercises. I do want to offer a note on time management as a kind of a success tip. This is true whether the course is offered in person or online, but it's a very lab work intensive course and it does require you to manage your time. Make sure you're familiar with the syllabus, which is subject to minor changes, specifically things like a due date or something, but that will be announced as needed with plenty of time in advance. You're still responsible for knowing when that update is, but it's something that will definitely be communicated. So I want you to be prepared for knowing when you need to go to lab and what you're going to be looking at and when an exam is going to be and all of these. If there's a deviation from the syllabus, I'll be posting it on Canvas immediately or making a class announcement. As far as the grading goes for the class, scores won't be curved because usually it doesn't need to. Usually my averages for a class is in the mid-70s, and that's actually pretty good for an intro course. So it's your kind of typical 90, 80, 70, 60 scale. Anything below 60% is considered an F, but hopefully we won't have to worry about that at all. I do want to bring up a couple of little things that may seem trivial, but it is actually quite important, and one of them is email etiquette. Please draft your email messages in a professional manner. If I see something that's coming in that's really, really sloppy, and I don't mean like poor grammar necessarily, but just not professionally written, I make no promises that I'll respond. And what I mean is, my name isn't Hay, so please, when you're emailing me, let's use appropriate email dialogue. Introduce yourself. I actually teach a couple of courses here and also a few online courses at other institutions. So if you email me and just say, hey, I'm in your class, I'm not going to know what you're talking about. So I just need you to please introduce yourself. What class are you in? And we can go from there. So I'll be right back is a sentence. BRB is not. So if I need to Google your abbreviations, I'm not going to respond. I prefer to use what's called the Princess Bride model, for those of you familiar with the classic 80s film, where the character Inigo Montoya has a catchphrase, hello, my name is Inigo Montoya, you killed my father, prepare to die. This is actually a perfect greeting for networking success because it's a polite greeting. He introduces himself with his name, what is the relevant personal link, and then how to manage expectations. So I strongly recommend using something along those lines when you're emailing me. Just it's a way for me to help you if I know who I'm talking to and what this is about. Also, I do just want to mention on a personal note that I have 2 small children at home. I have a 10-year-old daughter and a 6-year-old son. So in order to maintain a functional work-life balance, or in order to try, I make no guarantee that any email sent after 6 p.m. will be answered until the next day. Now, I usually do find some time in the evenings to check email, and I will be doing that again, but just know that that's sometimes when my family stuff comes up and I won't be able to get back to you as quickly as I can. So it's not an I won't be answering emails after 6, it's just I can't promise that I'll be getting to it as quickly as I would otherwise. So I appreciate everybody's understanding in that. So I think it's good for any course to start out with some introduction of goals, so everybody kind of knows what page we're on. My goals as your instructor introduce you to the basic concepts and applications of paleontology and geology as we evaluate the Earth's history through the Mesozoic era with an intense focus on dinosaurs. Again, this is a geology course where we're emphasizing the role dinosaurs play in our understanding of the Earth's history. I will be grading your progress in learning these concepts and applications. Now, one of the ways that I can grade your progress is through exams and quizzes, which will all be online, and details will be given on those specific exams and quizzes as we approach those. But that's going to be my way of really gauging how well you understand the material. As such, not everything we discuss in class is going to necessarily be on an exam. I think that's a misconception that a lot of students have about testing. Is just because we talked about it in class does not mean it's going to be on an exam. I'm not going to tell you always what will and what won't. All the concepts are important to the subject. The goal here is to go over the material, and I will randomly select some of that material and put it on an exam as a way of gauging and grading your progress. Your goals as students enrolled in this course are to gain a basic knowledge of the science of geology and paleontology. Understand the history of our planet with an emphasis and a focus on the Mesozoic era, the time in which what we call the non-avian dinosaurs existed. Also, I would like you to be aware of the processes and resources of the planet Earth so you'll be an informed citizen. Okay. I'll be the first to admit that dinosaurs aren't curing cancer. However, understanding dinosaur evolution and understanding how we can interpret the fossil record gives us a much more vivid picture of Earth's history. And history is an important aspect for understanding how our planet works, how it has worked, and how we can notice when we deviate from some of those habits and patterns in our planet. So understanding the Earth is a very important part of it. Dinosaurs are kind of a fun, alluring subset of fossils, so we're going to use dinosaurs to help us learn more about the Earth. And with that, I welcome you to the class, and I wish you good luck. There are a couple of themes of this course I'd like to go over. One of the main ones is that in order to understand dinosaurs, or any kind of ancient life, if we're looking at any fossilized organism, we have to understand the world in which they lived in order to understand how they lived. So for example, if I were to give you the skeleton of a polar bear, completely out of context, you may have a hard time identifying it as an animal that is well adapted for cold tundra type climates, have a hard time identifying specifically what its diet is and what kind of environment it lived in. However, if we have a better picture of what kind of environment it is, then all of these other characteristics that we might see in that skeleton start to make more sense. So if we want to interpret ancient life, we have to first interpret the world in which that ancient life was living in. And if we want to understand the ancient world, we turn to geology. So one of the other themes of this course is that the Earth is a rather unique planet. Obviously not the only planet in our solar system, but we are most definitely a very unique one. Our planet is controlled more or less, or runs based on a complicated system of interactions between what we call different spheres. You may be thinking, what do you mean by spheres? Well, collectively, all of the gas that we have in our planet is the atmosphere. Okay, so whether it's the oxygen you're inhaling, mostly nitrogen by the way, and the carbon dioxide that you exhale, that's all part of the atmosphere. When you boil water, you are adding water vapor to the atmosphere. If you go to a dairy farm and you smell methane, that is part of the atmosphere. So our atmosphere changes from one location to another. It changes through time, both on a small time scale throughout the year and also on a much larger time scale. The atmosphere's composition has changed considerably over 4.6 billion years of planetary evolution. But it's more than just the atmosphere, it's also the hydrosphere, all of the water on the planet. Whether it's the water in your water bottle or the water that's flowing in the lake or the river or the ocean, all of that is part of the hydrosphere, the collective water on the planet. We also have a cryosphere, which is all of the ice on the planet. Now, this is part of the hydrosphere, and as you can probably imagine, this also changes throughout the year, especially in the Midwest. We have a considerable cryosphere during some of the winter months, and then that goes away in the summer. Antarctica goes through a cycle of varying amounts of cryosphere. Antarctica does have some melting every year, and then it gains just as much ice back later on in the year. So we also have a biosphere, and really this is the one that makes Earth unique. It's the fact that we have life on this planet, whether it's you, me, a chicken, a tree, whatever. Anything that's alive, even going all the way down to a tiny bacterium or possibly even viruses. All of this is part of the biosphere, and this is really the thing that makes Earth unique, is we don't know for certain any other planets that have this. We speculate, but we don't know for certain that any other planets have a biosphere. Another one is we have a geosphere. All planets technically have a geosphere, but ours is very unique as well. This is the Earth itself. This is the internal parts of the Earth's structure, the crust, mantle, core, the tectonics. That is all part of the physical geosphere. Okay. Now, the interaction that we have among all of these spheres, the life, the earth, the ice, the water, and the gas, we call the Earth system. And this is what makes Earth unique. We are the only planet that we know of that has a complicated interaction at any given time between gas, between water, possibly ice, between life, and between the Earth itself. So as you are sitting on your computer or smartphone, whatever device, you are interacting with part of the geosphere. Think of the metal components that go into that computer. That is part of the geosphere. You're a living thing, so you're part of the biosphere. You're a breathing living thing, which means you are currently interacting also with gas. You're inhaling and exhaling. If you're having a beverage, I guarantee it's part of the hydrosphere, unless you're not drinking anything with water in it. We are the only planet that has this type of complex interaction. We have an Earth system. So we can really boil it down to the Earth system is the interaction between the planet, the atmosphere, the gases surrounding that planet, the life, and the water. So here we have an image that was taken from Hawaii. What do we see in this image? Well, you can see some of the steam, water vapor, or the mist from the humid tropics. You can see the black basaltic rocks that are eroding, and you can see the plant life that's growing out of them, contributing to the breakdown. So we have biosphere in the form of plants, we have geosphere in the form of the rocks, and we have atmosphere, and having been to an area like this, it gets rainy, so there's a lot of hydrosphere as well. This is a great example of Earth system. All of these things are interacting at once, and they interact today. They interacted yesterday. They interacted 65 million years ago when T-Rex and Triceratops were walking around what is now Montana. The composition of the atmosphere, the temperature, the type of life may have changed, but we still had an interaction of life, earth, water, and gas. So when we look at the Earth system a little bit more, there's this interlinkage, right, between living things, the biological, and the physical, the Earth itself. That's really what makes it unique, because we don't know of any other planets that have life. We have planets with ice and water and gas, but not like Earth. So this Earth system has gone on for a long time. Ever since we've had life, we've had an Earth system, but it changes. And there's different ways of discussing change in Earth's history through the Earth system. One, we can talk about the rate of change. Is this a slow, gradual change or a catastrophic change? Okay. Catastrophic change would be something like a massive volcanic eruption or an asteroid impact. A gradual change would be slow, like evolution, or usually things like climate change. But sometimes rates can change. You can go from gradual to catastrophic. The frequency, does this happen once or ongoing, or is it cyclic and repeating? So for example, bothering evolution again as an example. Evolution continues to happen. We don't see things starting over and re-evolving. We didn't see, non-avian dinosaurs evolve to birds and then back to dinosaurs and just keep going. It doesn't work like that. That would be a cyclic type change. We do see cyclic changes with the rock cycle. We see it with plate tectonics. We see it with the carbon cycle and the water cycle and all of these other types of cycles. These are changes that we're always in some stage of. Unidirectional changes, such as the formation of the Earth, happen once. They don't then hit the repeat button and do it again. And then what's the agency of the change in the Earth system that we can discuss? There are different agencies. Is it a geogenic change, meaning this is just a change that's happening within the Earth? Or, more recently, is it an anthropogenic change, meaning it's caused by people? So climate change, for example, there are geogenic aspects of it. There are certainly and clearly anthropogenic aspects of it. Okay, So we can discuss the way the Earth system changes over time in terms of how frequently does it change, what's the agency, and what's the rate. And changes can be both unidirectional and cyclic in manner. You can have cyclic changes, but then there's this overwhelming larger unidirectional change going along with it. So the formation of the solid Earth would be a good example of a unidirectional change. We start out with a very young homogeneous Earth that's just like a blend of different things as it's still very hot. And then as the planet started to cool off, the heavier material, the iron alloys, kind of migrated towards the center to form the core, and then the mantle remains much more rocky and iron-based, and then the crust itself is full of oxygen and silica. So we have a differentiated Earth that happened once as the planet was cooling. It was unidirectional, and then it didn't start over and do it all over again. Same thing with the evolution of life. Life appears kind of suddenly about 3.8 billion years ago, or GA, that's giga-annum, for billions of years. And living things have modified the Earth ever since. They've changed the composition of the atmosphere. You can thank small bacteria about a billion years ago for doing that. They've altered the chemistry of the oceans considerably. Think about how plant life affects the surface of the Earth, and plant life has not been the same. Did you know we didn't have grass on the surface of the Earth until about 90 million years ago? So prior to that, there was no grass. Now think about grass is very important today for holding ground together. It reduces rates of erosion. So we still had erosion happening, but at a much faster rate than today in some places. So these are all unidirectional changes. As things change, then we have a progression of fallout from that. But it doesn't all of a sudden stop and repeat. We're not going to see things go all the way back to the Precambrian and start all over again. Cyclic changes would be things kind of like the rock cycle. Okay, so we have three different types of rocks. We have igneous rocks, which are cooled from a melt, so magma or a lava. Sedimentary rocks are when we take any kind of pre-existing rock and we break it into pieces and then assemble it based on, it's kind of recycled. And then metamorphic rocks are pre-existing rocks that have been heated and squeezed almost to the point of melting, but not quite, but that transforms them. So this rock cycle gets complicated because if you have an igneous rock, you can break it down into a sedimentary rock, or you can heat it and squeeze it into a metamorphic rock. If you heat it and squeeze it too much, it becomes an igneous rock all over again. You can then take a sedimentary rock and heat it and squeeze it to a metamorphic rock, or melt it down. So all of these things can repeat. Hence why we call it a cyclic change. Another theme of the course, as we're kind of thinking about dinosaurs and their world, is that there are processes that change the Earth's surface inside the Earth and beyond the Earth. We have internal and external processes that interact at the Earth's surface. An internal process would be anything that relates to plate tectonics, anything like that. So this would be volcanism, earthquakes, when we form mountains, when we uplift or rift continents. All of these are types of internal processes. They start out with what's going on inside the Earth. External processes are related to an external source of energy. Now, what would be an external source of energy to the planet? It'd be things like the sun. And that amount of radiation we're receiving can affect weather, so rain, snow, and ice, and wind. And when we have internal processes like, I don't know, mountain building events, and external processes like weathering, interacting at the Earth's surface, we have a changing Earth. The planet's surface is constantly in flux. The stage in which dinosaurs and other ancient types of life lived was always in flux, sometimes slowly, sometimes unidirectionally, sometimes cyclically, sometimes catastrophically or gradually, but always changing. And life on that stage changes as well. Because geological phenomena affect the environment. And we've seen this even in our own time as a species on this planet relatively recently. So May 18th, 1980, before most of you were born, Mount St. Helens erupted. And you see the classic black and white image of Mount St. Helens. But if you actually were to look at the backside of where that image was taken, that's because you wouldn't be able to stand there. The blast of that was actually going up both up and outward. And so there was a considerable amount of ash fallout from this type of eruption. If you look at the distribution of ash around the continental United States, not counting Canada, from the May 18th eruption in 1980. You'll see we have trace amounts, which mean a dusting, all the way to a ½ inch of ash throughout most of Washington, parts of Oregon, Idaho, Montana, Wyoming, the Dakotas, going down into Colorado. I have no idea what's going on with Oklahoma. But yeah, huge amounts of fallout of ash. Now that is now incorporated into the geologic record. There's now a record of that eruption halfway across the country. One of the other themes of this course is that the Earth system is linked to life processes. As you remember, that's kind of the point of the Earth system, is that life is a major component. So life depends on the Earth. Living things like ourselves, we need nutrients, we need vitamins, minerals, and water, and we need all of these things to stay alive. But we end up changing the Earth as well, but it's in a sustainable way. So for example, dead plant material, in the fall that'll land on the ground, worms break that down into soil, and that helps further plants grow. Animals exhale carbon dioxide. Plants pull in carbon dioxide through photosynthesis and produce oxygen for living things like us to breathe. Microbes control more than we want to admit, which is kind of scary considering the world in which we're living in, right? The Earth system is linked to life processes. Life depends on Earth, and life alters the Earth, and the Earth then supplies life. So we have a sustainable model. Another really, really, really important theme for this course is about the scientific method. Science comes from observations, and we're going to be talking about science. This is a science class. Because dinosaurs are so popular, you do occasionally get a lot of arm waving, but that type of grandstanding has a tendency to get caught by real science and kind of put to bed. The more we look at dinosaurs as these big, cool movie monsters, the more people want to imagine cool things about them that necessarily is not always supported by science. So the scientific method really comes down to observation, right? You observe a phenomenon, or you collect facts about that phenomenon. You then analyze it and find some patterns, and then you start building a hypothesis. Now, most of us probably are familiar with hypothesis being defined as an educated guess, and I guess that's kind of accurate, but there's a better way of describing it. Hypotheses are ideas to be tested. Okay. If you want to know why your data that you've observed has a certain pattern that you've uncovered in the analysis, the hypothesis is an attempt to explain that. It's a test. So we test our hypotheses, and if it's confirmed, we've now created a scientific theory. And a theory is another word that's commonly misused in popular dialect. We use the word theory, unfortunately, in the same way we use hypothesis. If you're trying to fix something that's broken, you might say, in theory, this should work, and that is not what a theory is. A theory is an explanation. A theory explains why and how something happens. Hypotheses can support or refute theories. Okay? So you observe something, you analyze and find a pattern. You then ask, why is there a pattern? And you come up with an idea to test it. If the testing works, you now have some support for a theory of how that phenomenon is occurring. If the hypothesis fails, you go right back to observation. And I can tell you that most science does not get to theory. A theory is about as good as you can get in science. So scientific papers, scientific research projects, there's just an ongoing loop. We observe something, we analyze it, we build an hypothesis, we test it. That didn't work. Go back. What's the old phrase? Go back to the old drawing board. And you start it all over again. But when you finally have a hypothesis that's been confirmed, your work isn't done. You've just established a theory. Now you need to further test that theory. And this is something that people are doing. People are making scientific discoveries. And we support our scientific findings. Our scientific findings are supported by data, not anecdotes, not feelings, hard, boring facts. So most of you probably grew up with velociraptors, a common popular dinosaur. to see kind of the way you saw them in the first or second or third Jurassic Park movie, roughly 1990s, let's say. Okay, that's kind of the first time. Believe it or not, before this movie came out, before the original '93 Jurassic Park came out, not everybody knew what a velociraptor was. This was not the household name it is now. However, if we look at the other image we see here from 2014, this is a more updated scientific evidence-based reconstruction of Velociraptor. It looks very, very different. The hands are being held differently. It's covered in feathers. First of all, in the Jurassic Park films, velociraptors are not that big. We'll talk more about that later. We've gone from thinking of these animals as big, leathery skin lizards to more bird-like. And that is not just because we think it'd be fun to draw them that way. A lot of that artwork you're seeing here is based on scientific fact. It's based on evidence. So we have the Jurassic Park reconstruction of Velociraptor versus the more scientifically accurate reconstructions. And notice how small Velociraptor is. Yes, that's about as big as Velociraptor really got. Sorry to ruin your childhood. So, geology as a whole is the study of the Earth. It's not just the study of rocks, despite what you may have been told. Rocks are part of it, but geology is an interdisciplinary science. A geologist, if they're well trained in different subfields, can tell you a little bit about, let's say, the composition of the Earth and its components, which requires knowing a little bit of chemistry. They can tell you about the physical changes the Earth has gone through over time, which does require an understanding of math and physics, at least rudimentary. If you want to know about the history of life on a planet, a paleontologist can tell you that, but as my paleontology students will tell you as well, there's a lot of biology that goes into that. As we'll discover here too, there is a bit of biology here because otherwise we're just looking at weird things in rocks. And if you're a biologist who's studying fossils but doesn't know about geological concepts, now you've removed the context from there as well. If we want to look at the distribution of land and the interaction of our different Earth system spheres over time, that requires knowing a little bit of geography. So historical geology, which is kind of the larger branch of geology that paleontology and dinosaur paleontology falls under, is the study of the history of the Earth, and this includes all of these cyclic and unidirectional processes and life. But we're going to be focusing kind of our understanding of Earth history around this very cool group of animals, the dinosaurs. So why would we want to study the history of the Earth? Well, we live on this planet, right? And every human that's ever lived has lived on this planet. And every animal that we know of that's ever lived has lived on this planet. So this is home, right? As Carl Sagan said, this is the only planet we've got. So if we want to understand our place, our contextual place in this planet and in evolution over time, we should understand history of the Earth. If you want to study world history, it's to understand how we got to the society that we have. Well, if we want to understand Earth history, it explains how we got to the world that we have today. And geology is really the foundation of everything on Earth. Every building is that's built from stone has a geological fingerprint on it. Even the type of rocks we're building our skyscrapers on top of has a history. Okay? Behind every ecosystem, the speciation of every new organism, human achievements, geology is setting the stage. But why study dinosaurs? Why are dinosaurs important? Well, what I want to talk a little bit about here is, kind of a preview, a little bit of the history of the study of dinosaurs. And then what dinosaurs are and what they're not. When did they live and where did they live? We know about the dinosaurs of the Mesozoic era because of their fossils. Now, that could be bones, that could be teeth, that could be claws, it could be impressions of skin and feathers. It can also be their footprints, their fossilized poop, bite marks, claw marks, any evidence that these animals were around. But the word fossil is rooted from the Latin fossilium, which loosely translates to English as dug from beneath the surface of the ground. So back then, anything that was being pulled out of a pit could be considered a fossil. Earliest usage of the word fossil really meant anything that is found in soil or rock. Around the 18th century, though, it started being kind of cornered to describe the remains of an ancient shell or bone. And that's still fairly accurate. However, we also include things that aren't parts of the animal or plant. So more than shells or bone or fossilized wood, but also traces like footprints. The modern definition really says any evidence of past life. That's a fossil. Any evidence of past life. But that's pretty vague. It's a pretty gray area when you think about that definition. You know, what does that really mean? Fossils are any preserved trace of past life. Any preserved trace of past life. This could be a footprint. This could be a bite mark. This could be the actual parts of the animal, like a carcass, or a dead tree, or a leaf, or a bug. But we have cemeteries full of dead people. How is that different? Well, the other part of this definition, naturally protected from rapid degradation. Naturally protected from rapid degradation. So if somebody passes away and we bury them for a funeral, that's not making them a fossil because we're doing it intentionally. Now, if a fish is swimming around and it dies and falls down to the bottom of the sea and it gets buried under sediment just because sediment happened to be falling in that area, that has the potential to become a fossil. It has been or has the potential to be naturally preserved inside of a geologic context. Okay. Notice here, none of these definitions describe anything about age. Age is not that important. Yet I've been to museums and looked at their signage, and some of them say something has to be so many thousands of years old to be a fossil, and that's total crap. That's not true. Something as young as a few hundred years old can be a fossil. In fact, some small single-celled organisms that live in the oceans are so tiny, and they make little glass shells out of them, out of the silica in the seawater. These are things called diatoms. And when they die, it takes so long for them to fall down to the bottom of the ocean. It can take literally centuries for it to finally hit the bottom. Now, it's been dead for centuries. Okay, and it naturally is just slowly falling. That is also considered a fossil. It's important to remember that when we're talking about fossils, whether it's bones or shells or whatever, most of the fossils that we're seeing represent a subset of the original animal or plant. We're looking at the bones, we're looking at a shell, we're looking at a tooth. But think about you yourself. You have bones and teeth. These are the hard parts of your body, but that's not all of you, right? That's not all of you. The soft tissue parts, your skin, your organs, your brain, your heart, all of those things are what make you, a living thing. Mineralized tissues like bones and teeth grow in response to soft tissues. So when we are all, as humans, gestating in our moms, during 9 months, we have a brain before we have a skull. We have a heart before we have a rib cage. So hard parts grow around soft parts to protect them. That's why we have a rib cage and why we have a skull. So when we look at fossils, all we're seeing is that leftover hard part. And we have to remember this formed when that animal was alive in response to the really important parts that these bones were trying to protect. Okay, so we rarely find complete skeletons. And even if we did, that's still not the complete animal, right? We're missing the vital parts that make that thing be, that made it alive. But we can still learn a lot from those bones. So this is why paleontology, and especially dinosaur paleontology today, requires a lot of comparisons with modern animals that are related to dinosaurs, like birds and crocodiles. We study their skeletons and their soft tissues, and then make comparisons from their skeletons to the dinosaur skeletons, and then try to make some educated inferences about soft tissues. So it's not a total shot in the dark, but we have to know which organisms to make comparisons to. Let's talk a little bit about the first dinosaurs, meaning the first ones that were discovered. This is an illustration of the very first dinosaur fossil ever found, or at least described. It was not thought of to be a dinosaur. In fact, it was thought to be parts of a giant human male. In fact, the proper name of this described specimen is Scrotum humanum from 1677. Now, I bring this up not only because it's kind of amusing, but this was found out later to be the thigh bone of a much larger non-human animal, a dinosaur actually. So it was a large meat-eating dinosaur. It was part of the distal end of its thigh. Now, what about the history of the study of dinosaurs, kind of going beyond the 1600s? The word dinosaur was first coined by this man, Sir Richard Owen, in 1842. It comes from the Greek word dinos, which means terrible, and sauros, which means reptile or lizard. So dinosauros or dinosaur means terrible lizard. And Owen, Sir Richard Owen, was one of the first biologists to really start looking at these fossil bones people would bring him and started realizing, no, they're not parts of giant humans. These are actually skeletal elements to larger, more, I guess, reptilian type animals. So Owen's first dinosaurs, the first ones that he described and kind of put under this large umbrella of dinosaurs, the first one was Megalosaurus. Megalosaurus is a rather large carnivorous dinosaur from the Jurassic period, so 167 million years old. We have them in England. We also have types of megalosaurs in the Jurassic rocks of North America. A really big one called Torvosaurus we'll talk about later in the semester. And there's not much of this first Megalosaurus specimen. You pretty much have a jaw with a tooth. But it was enough to get an idea, again, making comparisons to modern animals, that it is more reptilian than it is mammalian. We also had Iguanodon, which was actually discovered by a man, well, his wife, Gideon and Mary Mantell, who brought these fossils to Owen, and he described them as Iguanodon, which means iguana tooth, because one of the first bones they found of this large herbivore was a tooth that looked very similar to an enlarged iguana tooth. So because the tooth looked like it, they imagined this animal looked like a great big iguana. And then there's Hylaeosaurus, which is one of our armored dinosaurs. It was one of the first described dinosaurs, and it's one of these ankylosaurs or nothosaurs, which have a lot of armor plates and spikes on their back. And these were all the rage. When Owen was releasing his studies based on these very scrappy elements of Hylaeosaurus, Iguanodon, and Megalosaurus, people really didn't know what to think. These were really terrifying monsters to consider that at one time lived in Earth's history. In England, even today, not terribly far from Buckingham Palace, you have the Crystal Palace dinosaurs. These were, at the time, considered to be life-size models of Owen's dinosaurs. So here you have the Crystal Palace version of Megalosaurus, that fossil known from the jaw and the tooth. These are the Crystal Palace iguanodons, and they're still there today. Unfortunately, one of them was recently vandalized, but it is being repaired. And here is the Crystal Palace Hylaeosaurus. Okay, so these are still in the gardens of the Crystal Palace in England. Now, we know a lot more about these animals now than we did in the 1800s. So this is now what we think Megalosaurus looked like. And again, that lower portion of its thigh bone is what was once called Scrotum humanum. So here's Megalosaurus. That's an iguanodon, and notice the scale bar there, that is 6 feet. So this is a rather large animal. And there is Hylaeosaurus, this armored dinosaur. So honestly, out of all of them, they were closest, I think, with Hylaeosaurus, but still really, really, really far off. But it just shows how the history has changed over time because we found more specimens. That original iguanodon was known from just a handful of bones. We now have dozens of specimens of iguanodon and have a much better idea of what the animal looked like. So what is a dinosaur and what isn't? Because as we go through Mesozoic life, we are going to talk about dinosaurs a lot, but we also want to talk about things that are commonly called dinosaurs but really aren't. And pterosaurs are at the first of the list. Flying reptiles. These are not flying dinosaurs. We used to say dinosaurs didn't fly, but now that we know dinosaurs and birds are pretty much one and the same, yeah, some of them do, but the ones we think of from the Mesozoic, the big T-Rexes and things, no, they didn't fly. Pterosaurs are not actually dinosaurs. They're cousins. It would be kind of like looking at the difference between rodents and rabbits. They're clearly related to each other, but they're not the same. You wouldn't say that rabbits are in the same group as rats. Okay, there's a separation there. There is a difference in number of characteristics, and the same is true for pterosaurs. Pterosaurs they don't have all of the characteristics that we call for dinosaurs, but they are close cousins. The aquatic dinosaurs are not dinosaurs. Things like Plesiosaurus and Kronosaurus and the mosasaurs that you may have seen in the Jurassic World films. These are not actually dinosaurs. They are marine reptiles. In fact, they're very, very distantly related to dinosaurs. In fact, going back hundreds of millions of years. So they're really not the same thing. Some of these do have living relatives today. For example, some of the things called mosasaurs, again, like you may have seen in the Jurassic World films, are distantly related to things like Komodo dragons. So they're not the same. They lived at the same time, but they lived in the water. Dimetrodon, you may have seen this animal before. This is actually not only not a dinosaur, it's not even really a reptile. These are more closely related to us, which seems totally bizarre and unlikely. But when we look at the skull structure of a Dimetrodon, which, by the way, lived before the dinosaurs, the last Dimetrodon died before any of the first dinosaurs appeared, we now actually can trace our own mammalian skull lineage back to Dimetrodon. Dinosaurs are on the other side of the family tree. Woolly mammoths. I don't know who said these are dinosaurs, but I've seen it in kids' books, and I've heard people say that it's like a dinosaur. Just because something is old and extinct and big does not mean it's a dinosaur. These are obviously more closely related to elephants, and it's an actual mammal. So, not there. Now, crocodiles. Crocodilians, like alligators and caimans and crocodiles themselves, are commonly called living fossils, which is just kind of a silly phrase because they have evolved quite a lot over time. But these are distantly related to dinosaurs, but they're not. These form one of the groups in which dinosaurs are nested in. It's a group called Archosauria that we'll talk more about this semester. And dinosaurs are kind of the oldest group in Archosauria. Birds are one of the newest groups, and the rest of the dinosaurs kind of fit in between. So again, they're cousins, but we do study crocodiles to get an idea of dinosaur physiology, but we also balance it by studying birds as well. So how do we define a dinosaur? Well, there's a lot of different characteristics, but just for today or this week, I just want to cover a couple of the basic ones. One of the first things you can notice is the posture. Dinosaurs, whether it's a T-Rex or a Brontosaurus or a Diplodocus, all have an upright posture versus the sprawling posture that we see with reptiles like lizards. So notice when we look at the dinosaur in the image, you're seeing a side view and also an arrow view looking down. The legs are underneath the body. Well, if we look at our Komodo dragon there on the right, the legs are sprawled out. So that's a reptile characteristic. Our crocodiles do that, our lizards do that. Dinosaurs held their limbs directly under the body, just like modern day birds. But there's a lot of other features. There's how many extra holes are in the skull, and what kind of ankle bone they have, and what's going on with the hip socket, how the limbs are held, how many vertebrae they have in their pelvis. These are all the characteristics we use to say something is a dinosaur versus something else. If it has most of the characteristics, but it's missing one or a few, we call it a dinosauromorph. It means it's almost a dinosaur, but not quite. So when we look at things like crocodiles, they don't share many of these characteristics, maybe one or two. When we look at birds, they share a lot more. We look at mammoths, they don't share any. So we'll talk more about these 6 main characteristics that we use to define Dinosauria in an upcoming lecture. So when and where did they live? Where did dinosaurs live? Well, not all dinosaurs lived at the same time. One of the weirdest things about the Jurassic Park movies is the word Jurassic is just, it is a geological time period, but they used it for that movie and for those books because it's catchy. Okay, they could have used Cretaceous or Triassic. Those are the 3 time periods in which dinosaurs lived during the Mesozoic era. You have the Triassic, which started about 252 million years ago, And then you have the Jurassic and then the Cretaceous period, which ends about 66 million years ago. We have 3 different time periods because we have 3 different types of dinosaurs and life in these time periods. So T-Rex, for example, lived in the Cretaceous. Brontosaurus and Stegosaurus lived in the Jurassic. Things like Coelophysis and Plateosaurus lived in the Triassic. So they didn't all live at the same time. But notice the amount of time we're talking about here, from 252 million to 66 million. These are very successful animals. They didn't all live at once. They didn't all share the same block of time. But the era in which, the Mesozoic era in which the non-avian dinosaurs were prolific, was a considerable amount of time. It's a huge chunk of Earth's history. So here's a perspective of when we're starting to see these different groups. Stegosaurus, the large plate-backed spike-tail plant eater from the Jurassic period, lived from about 155 to 150 million years ago, late Jurassic. T-Rex lived from about 68 to 66 million years ago. Human beings, Homo sapiens, kind of the way that we would recognize Homo sapiens, around 350,000 years ago. So when you think about it, 150 to 155 million, 68 to 66 million, and 350,000, when T-Rex was alive, every single Stegosaurus was already a very, very old fossil. And T-Rex is closer in time to us and our technology like the iPad than a Stegosaurus is. So next time you see an illustration of a T-Rex fighting a Stegosaurus, be sure to call out the BS on that one, because they did not all live at the same time. The Mesozoic era is a huge chunk of time, but not all the dinosaurs lived all at once. And where do we find them? On every single continent. Now, part of why we see so many clusters of dots in some places and not others does have to do with what people are looking for. It has to do with geography. It also has to do with politics and economics. So, for example, there haven't been many found in Antarctica, but that's because most of Antarctica is under a lot of ice and it's very, very hard to work there. It's also very expensive to get there. However, we do have them up in the Arctic. We have them on all the continents: South America, Africa, Australia, Asia, Europe, and North America. Notice we have a lot of finds in North America because we're free to go look for them in a lot of places. In Asia, there's a lot of dinosaur fossils found, but you have to go through certain channels to get permission to go there. Same thing with various parts of Africa. South America, a lot of that's so heavily covered in jungle, it's hard to see anything, but when you go to the Patagonia region, you do start finding some really amazing things. So they are widely distributed around the planet. There's just a couple of reasons why maybe we haven't uncovered every single one of them yet. So why should we study dinosaurs? Why should you continue to stay in this class? Well, because these are a great example of evolutionary success. Notice the branching we see on these family trees here, going from the Triassic period where we start out with a couple of dinosaurs, and then in the Jurassic we see those branches branching out to more branches and more, and in the Cretaceous even more and more. So there's this wide diversification of dinosaurs. So if we want to understand the importance of evolution, this is a great group of animals to study, because we have a good enough record to see how vastly different they can become over time. They can also then offer a guide to evolution. As I've already mentioned, dinosaurs and birds are closely related, and that's an understatement. Birds today, living birds, the chicken that you eat, the birds at your bird feeders, are living dinosaurs the same way that we humans are a type of primate. No, we're not monkeys. No, we're not chimps or gorillas. We're Homo sapiens, but we're cousins with those other animals. We all collectively are primates. Birds and T-Rex are all dinosaurs. And we can use the evolution of dinosaurs to help us understand about how evolution works. We can look at things like Sinosauropteryx and Velociraptor and Caudipteryx and Archaeopteryx itself, and go all the way to modern day Corvus or crows. And we can see how these subtle changes over millions of years transformed theropod, meat-eating dinosaurs into a new form of modern day birds. So we can use dinosaurs as an example. And there are other things we could use too. We could use the evolution of horses, the evolution of whales, the evolution of humans. But it's yet another great example of how evolution actually works. And another reason to study dinosaurs is because they're really interesting, right? These are real life monsters. And especially for those that might be going into education, this is a fantastic way of getting kids interested in science. As I already mentioned before, geology in general is a great gateway to learning different aspects of science. You want to know a little bit of chemistry, a little bit of biology, a little bit of physics, a little bit of math. And paleontology and dinosaurs are, I mean, let's be honest, they grab people's attention, especially kids. Some of us never get over that. But it's a way of getting that attention onto natural science, and we can then start to learn more about the real science as we get into this. So dinosaurs are important for scientific literacy. It helps us become a smarter society by studying something that we need to branch out in that field to get out to these other aspects of science. Astronomy is another good one too, but astronomy doesn't have big things with teeth that we know of. So why study dinosaurs also? Because we already learn from nature, right? We study living animals to understand how to better produce a society that's productive. You know, we look at how certain kind of caterpillars will spin silk as a way of us to improve the way that we make textiles. Dinosaurs did some amazing things, just like modern day animals do amazing things. But the way that these long-necked sauropods almost act like a crane, well, how could we maybe study this animal, its fossils, and make a crane even better? How could we study something like the Pachycephalosaurus from the Cretaceous period and make a better football helmet? Okay. So some of these may seem like flights of fancy, and perhaps they are. But just as we study modern animals today to make our society better, ancient organisms are still on the table as well. So that kind of wraps up the introduction to the course. This is the first week lecture. Next week, we will be looking at evolution, extinction, and more aspects about the fossil record in general. So what I would like you to do, please, is look at the Lucas textbook, chapters 2 and 3. And I'll be posting the lecture before at the beginning of the week. And you'll have all week to review it, go through it a couple of times, and come up with any questions. You can email those to me. You can talk to me about them in lab, or once I get a date set for that review session, we'll start doing that as well. So any questions you have, feel free to email me. If you want to set up a time to visit virtually or in office hours, again, shoot me an email, and I'll be happy to accommodate that. So this is the lecture for week 1, and we'll talk to you soon.